In PV1X, we discussed the fundamentals of photovoltaics. Starting with energy in general and solar energy in particular, we dived into the semiconductor physics and optics required to understand all the loss mechanisms that take place in a solar cell. In the next few videos, we would like to remind you of all the content covered in the PV1X photovoltaic energy conversion course. If some topics seem unfamiliar, we encourage you to return to the PV2X course and revisit those topics before attempting the practice of proctored exam. This overview shows all the losses that take place in a photovoltaic device. The losses can be grouped into optical and electrical losses. We will start with a recap of the electrical losses and in particular the recombination losses that are described by semiconductor physics. A semiconductor is a material whose conductive properties are between that of a conductor like metal and an insulator. In PV1X, we have generally used silicon as an example, since it is the most used semiconductor in the PV industry by far. A solid like silicon can be either monocrystalline, polycrystalline or amorphous. Monocrystalline solids are highly organized structures where atoms form a continuous crystal lattice. In polycrystalline solids, regions of crystallinity are present with different sizes and orientations. These small crystals within the lattice are called grains or crystal domains. Amorphous solids are materials in which no crystallinity can be observed. Semiconductors have a certain bandgap energy. This is the energy required to excite a valence electron to a conducting state. An insulator is a material with a very large bandgap energy. A conductor is a material in which the energy levels of the conduction and valence band overlap. The bandgap energy is the energy difference between the valence band edge, the upper energy limit for valence electrons, and the conduction band edge, the lower energy limit for conducting electrons. In between these band edges there are no states for an electron to occupy. Materials with an indirect bandgap energy require a phonon as well as a photon to excite an electron, which means they generally have a lower excitation probability than direct bandgap materials. The energy band diagram, as it is shown here, only tells whether states are available at a certain energy level. To answer the question how many states are available, we look at the density of states function. This function is material dependent. The density of states function therefore tells you the number of states available for an electron to occupy at a certain energy level for a given material. As you can see in this figure, in high purity intrinsic semiconductor materials there are no energy states available for an electron to occupy in the bandgap. To find out about the occupation of the energy states, we need the Fermi-Dirac distribution function. This distribution gives the probability that a certain energy state is occupied at a certain temperature. The Fermi-Dirac distribution is a general rule applicable to electrons in all kinds of systems. With these in mind, we can determine the charge carrier densities in the conduction and valence bands. This is what the profile of the occupied states look like. On the top we can see the occupation of the conduction band states and on the bottom we see the occupation of the valence band states. In fact, the Fermi-Dirac distribution describes the probability of a state being occupied with respect to the Fermi energy level. The Fermi energy level can be loosely interpreted as the average energy of the valence electrons in the material. In an intrinsic semiconductor, the Fermi energy level is in the middle of the bandgap. This changes when the semiconductor is doped with dopant atoms. N-type dopants have an additional valence electron with respect to the intrinsic lattice, while p-type dopants have one fewer electron. When integrated in the lattice, N-type dopants therefore produce an additional free electron, while P-type dopant introduce an additional hole. Moreover, ionization of dopant atoms can locally affect the charge neutrality of the lattice itself. This happens when mobile carriers, electrons and holes, deplete the region with fixed ionized dopant atoms. As a consequence, the lattice will become locally positively charged in the N-type, while in the P-type it will become negatively charged. Now, when inserting donor and acceptor atoms, properties like the Fermi-Dirac distribution and Fermi energy levels will be affected. Let's see how. Since by N-type doping we increase the number of electrons with energy in the conduction band, the average energy of electrons will increase. This will result in a shift of the Fermi levels towards the conduction band. If we look at P-type material, we can see a similar but opposite effect. Due to the presence of additional holes, or in other words, due to a relatively higher fraction of electrons being covalently bonded, the Fermi level is shifted towards the valence band. The higher the doping with acceptor atoms, the closer the Fermi level will be to the valence band. We call the carriers whose concentration is much larger than that of the other type majority carriers. These are holes in P-type materials and electrons in N-type materials. Minority carriers therefore are electrons in P-type and holes in N-type materials. So far we looked at semiconductors in the dark, under thermal equilibrium. Now let's illuminate the material. We have now much more electrons occupying states in the conduction band and much more holes occupying states in the valence band. The Fermi level is used to determine the concentration of both electrons and holes at thermal equilibrium. Going from equilibrium state to a non-equilibrium state, such as under illumination, we use two quasi-Fermi levels, one for the holes and one for the electrons. A consequence of this situation is that the mass action law does not hold and the product of concentration electrons and holes is not anymore equal to the density for intrinsic situation, Ni squared. But how exactly do these free charge carriers move? Two main mechanisms of carrier transport in solar cells are drift and diffusion. Drift is a term used for charge transport that results from the interaction between charged particles and an electric field. If an electric field is present, holes will move in the direction of the field and electrons will move in the direction opposite to it. On the other hand, diffusion is based on thermal motion and driven by a concentration gradient of charge carriers. Carriers will randomly flow in all directions. However, more carriers will randomly flow from the high to the low concentration region than the other way around. This results in a net flow of carriers to the low concentration region, giving rise to a diffusion current. At thermal equilibrium, the generation rate of charge carriers is balanced by the recombination rate. There are three ways in which this recombination occurs. For radiative recombination, the energy of the electron is emitted as a photon after recombination. The energy of this photon is the same energy as the band gap energy of the semiconductor material. Radiative recombination is very significant in direct bandgap semiconductors, but relatively rare in indirect bandgap semiconductors like crystalline silicon. Auger recombination, on the other hand, is a three-particle process. The momentum and energy of the recombining hole and an electron are transferred to another electron or another hole. This third particle is excited deeper into the respective band and relaxes again by a process called thermalization. In this thermalization process, this free electron in essence loses some of its energy in interactions with the lattice. The third process is Shockley-Read-Hall recombination. Shockley-Read-Hall recombination is indirect and is facilitated by an impurity atom or lattice defect. These recombination centers introduce energy levels within the band gap, which facilitates carrier recombination. Radiative, Auger and Shockley-Read-Hall recombination are the three ways in which excited charge carriers recombine. At the surface of a semiconductor where the crystal lattice terminates, many valence electrons cannot find a partner for creating a covalent bond. This results in so-called dangling bonds. In the band diagram, these defects are represented by energy levels in the band gap, which will induce Shockley-Read-Hall recombination. In fact, for semiconductors that hardly have any defects in the bulk of the material, the recombination might be dominated by surface recombination. These dangling bonds are also present at interfaces between different materials, for instance because the lattice of the two materials might be mismatched. However, making an interface with another material might reduce the defect concentration at the surface. An indicator of the total recombination is the recombination current density, J0. To keep track of all the generation and recombination, we've introduced you to the ambipolar transport equation. In this slide, a volume element is shown of a semiconductor with sites of dx, di and dz. The transport equation is in essence a way of bookkeeping of charge carriers. The equation describes how the electron density changes over time due to diffusion and drift and in out of this finite element and due to generation and recombination inside this element. This covers the working principles of semiconductors. In the next video, we will do a quick recap of the p-n junction.